Hello, I'm Rachel Parziali. In this video, I'll be going over the paper Universe, Opacity and CMB by Václav Vavryčuk, printed in the monthly notices of the Royal Astronomical Society. I originally read this paper under my advisor, Dr. Pavel Krupa, at the University of Bonn. In this video, we'll just go over the main points of this paper and what it means and the implications for the current cosmological model. We'll start by looking at the abstract of this paper. Now this is a very long abstract, as you can see, so I won't read it word for word in this video, but I'll leave it here if you want to see it, and I've also linked the paper in the description of this video if you want to read it yourself. But instead, I'll just go over a few key points of this abstract. Now, of course, this paper is talking about the cosmic microwave background, or the CMB, and in particular, it's talking about a theory where the CMB is not due to the Big Bang, it's not a relic of the Big Bang, but instead looks at a theory where the CMB is thermal radiation from intergalactic dust. And it goes through this dust theory for the CMB, and it looks at how it could explain the different characteristics of the CMB we see today. For one, it looks at how this dust theory could explain why the CMB is a black body with a single temperature, and what the predicted temperature of the dust would be in this theory, which is 2.776 Kelvin, and how that compares to the current CMB temperature. It then goes on to look at the temperature fluctuations of the CMB, and in the dust theory, it explains these fluctuations using clusters and voids in the universe, and the EBL fluctuations those cause. It also looks at the polarization fluctuations of the CMB, and again, in this dust theory, it explains them with clusters and voids and the large-scale magnetic fields around them. Now, before we get into the rest of this paper, I'll give a brief little background and introduction on the subjects of this paper, starting with the CMB itself, of course. First discovered in 1965 from Penzias and Wilson on their radio telescope after they observed this strange background radiation wherever they looked. Of course, now we've measured it a lot more accurately. We've made this map. This is a W map of the CMB you can see here, with the color bar indicating its temperature fluctuations. We've now measured a temperature for the CMB as 2.725 plus or minus 0.00057 Kelvin. We've measured its large-scale temperature fluctuations of plus or minus 0.00335 Kelvin. And on small scales, it has temperature fluctuations of plus or minus 70 microkelvin. Now, of course, since we've discovered the CMB, there's also been theories on explaining the origin of the CMB. One you might have heard of already is the hot Big Bang theory, one of the first theories to be put forward to explain the CMB, because in the hot Big Bang theory, it already predicted that there would be black body radiation. And in this hot Big Bang theory, it explains the polarization fluctuations due to Thomson scattering of a local quadrupole radiation pattern by free electrons during the last scattering epoch. And the temperature fluctuations in this theory, the peaks correspond to cosmological parameters such as the curvature of the universe or dark matter density. But, of course, this is not the only theory for the origin of the CMB. Like I said, there is this dust theory that this paper looks at, where instead of the CMB being due to the Big Bang, it's due to this surrounding intergalactic dust that's been thermalized by starlight and is now re-radiating back at us as what we see as the CMB. And in this theory, the universe is opaque at high redshifts, and the anisotropies in temperature and polarization are due to clusters and voids, which we'll talk about more later. Now, why is this paper examining this different theory for the origin of the CMB? At this point, the CMB is even seen as supporting evidence for the hot Big Bang theory, but as this paper points out, there is still some drawbacks or unanswered questions to the hot Big Bang theory. For one, this only applies for transparent universes. The hot Big Bang theory does not take into account the radiation of intergalactic dust, which we know is there. There is dust between galaxies. In particular, this paper cites another paper that's measured the effective dust density, which you can see here, just to demonstrate that we do know there is intergalactic dust between galaxies. We can measure it, and it is something that needs to be taken into account and was not in the hot Big Bang theory. And the CMB has some non-Gaussian structure on large scales, which is not included in the hot Big Bang theory. Now, of course, the dust theory has some unanswered questions as well, such as, well, if there is this intergalactic dust that exists at different redshifts and different temperatures, then why does the dust radiate as a black body at a single temperature? Why is the CMB so isotropic? Why are the temperature and polarization anisotropies correlated here? And again, why is the CMB not affected by redshift if the dust is found at these different redshifts and temperatures? Now, answering these questions is the main goal of the paper, just going through these and establishing how the dust theory can address each of these questions. In particular, it goes through these 5 characteristics of the CMB and our measurements of them, and addresses how the dust theory could explain the measurements of the CMB we have for these. And the first one it starts with is the temperature of the CMB. Now he starts addressing the temperature of the CMB by talking about extragalactic background light, or EBL, which is basically the light emitted from galaxies. And of course, like all light in the universe, it's redshift dependent, according to this equation he cites here. And here on the left, we have a plot of this EBL, where it's wavelength versus intensity on the y-axis versus wavelength on the x-axis. And all these symbols shown here on the right correspond to different papers that have measured the EBL intensities. And you can see the 2 peaks in this graph, one in the visible range for starlight and one in the infrared range due to the emission of dust in the galaxies. And this whole thing, you should note, goes from ultraviolet to visible to infrared wavelengths, but does not include microwave wavelengths. So the CMB is not included in this plot anywhere. Now what he's done here with this EBL plot is he's drawn in these 2 black curves to denote the maximum and minimum values of the EBL. And he says based on all of these measurements of the EBL, he found the most likely values for the EBL based on these upper and lower limits. He says the total EBL should fall between 40 and 20 nanowatts per meter squared per steradian, with the most likely value of the total EBL falling between 80 to 100 nanowatts per meter squared per steradian within this wavelength range. So now that he has defined this most likely value for the light from galaxies, this EBL, he applies it to this sort of cycle theory here, where you have the EBL, you have galaxies radiating out light. That light in turn is absorbed by the intergalactic dust. Then the dust will re-radiate that light back out, and it'll be absorbed again by the EBL. And in this little cycle theory, the total energy radiated by dust is equal to the EBL absorbed by the dust. He says here that this whole cycle should already be in thermal equilibrium because the dust grains are small enough. If it was not in thermal equilibrium, you'd have this scenario on the left here, where these ellipses represent galaxies, and the gray matter between them represents the intergalactic dust, where the galaxies are just emitting, and that's being absorbed by the dust and heating it and raising its temperature. But again, he argues that these dust grains are so small that this will very quickly reach thermal equilibrium, and instead you'll have the scenario on the right, where the galaxies are emitting light to be absorbed by the dust, which then re-emits that energy and is absorbed by the galaxies again. So using that cycle from before and his EBL estimates he established, he can now use all this to estimate the temperature of the dust in this condition. And the estimated dust temperature is 1.22 to 1.82 Kelvin, which, if you remember the temperature of the CMB from before, this is obviously not equal to the 2.725 temperature we've measured for the CMB. And he's illustrated that again in this plot here to the left. This is the same plot as before, where these two blue curves are the maximum and minimums he defined for the EBL, and this red curve on the right is the contribution from the CMB. And it can be seen that this contribution from these two blue curves cannot account for what we see in the CMB. It cannot account for the temperature we see in the CMB by itself. So the conclusion is that there must be something else that's heating the dust as well. So what he does is he adjusts that cyclical-like theory we talked about before, where again you have the EBL radiating out energy. It's absorbed by the dust, which will re-radiate out that energy. And again, some of that will be absorbed by the EBL, but some of that will be reabsorbed into the dust itself, and the dust will heat itself up too. Now, how much that's absorbed by the EBL and how much that will be absorbed by the dust, again, depends on the opacity ratio between the two, which is controlled by the distribution of intergalactic dust. So using Eller's measurements of this opacity ratio, he can then again estimate what the temperature of the dust will be. He now predicts a new temperature for the dust, and that new dust temperature is 2.776 Kelvin, which is now a lot closer to the 2.725 Kelvin we've measured for the CMB today. And he says, given the uncertainties in the EBL measurements, that this prediction for the dust temperature is a good match with the measured CMB temperature. So with that, he says, the dust theory can explain the measured temperature of the CMB. He now moves on to talk about that the CMB is a single black body spectrum and how the dust theory can explain this. We do know that the CMB is a very nearly perfect black body. You can see that here on the plot on the left, where we plot intensity versus wavelength. These dots are CMB data, and this black line it's plotted over is a black body spectrum at a temperature of 2.728 Kelvin. And you can see that the CMB data very closely matches this line. It's almost a perfect black body. So the challenge then comes in with the dust theory. When you have this intergalactic dust at different redshifts, and we know that redshift will affect the intensity of the dust, the temperature of the dust, and the frequency of the dust, then how can this dust be viewed as a single temperature blackbody spectrum, where the intensity, temperature, and frequency all vary with redshift according to these equations he's defined here, where I0d and T0d are the values of the intensity of the dust and temperature of the dust at z equals 0. So, given how intensity, temperature, and frequency all change with redshift, how can this dust theory explain why the CMB is viewed as a single temperature black body? The first assumption he starts with is that the dust is radiating as a black body. He does acknowledge that for small spherical dust grains of less than 1 micron in size, that these are poor radiators of millimeter wavelengths and that these would not be radiating as a black body. But he also cites several papers, like this one from Wright in 1987, that when you look at conducting needle-like dust grains or fluffy fractal-shaped dust grains, here are a couple examples of what those dust grains would look like here, that these are sufficiently opaque at these wavelengths and that these could radiate as a black body in the wavelengths needed for the CMB. So if the dust is radiating as a black body, it will now have this equation for its intensity, a black body intensity equation. And now if he puts in the parameters above and how they vary with redshift, he can do the math out. And then after doing the math out, the main conclusion is here, that all the dependencies on redshift have canceled out in the end. The temperature increase with redshift exactly eliminates the frequency redshift dependency, and now it will appear as a single temperature black body, just as we've observed in the CMB. So now with that, he says that this dust theory can explain why the CMB is seen as a single temperature black body spectrum. Now the next characteristic he talks about is the temperature anisotropies of the CMB. Now, we said before that the CMB is a very nearly perfect black body, but it's not perfect. It still has some temperature fluctuations. You saw that on the CMB map from before. Now, in this dust theory, he explained those temperature fluctuations using clusters, superclusters, and voids in the universe. Now, we know there's not a homogeneous distribution of galaxies in the universe. Like I said, there's clusters, superclusters. You can see an example of one here on the right, the Virgo supercluster, and voids. Here on the left, you see the same thing. Here's a map of the distribution of galaxies in the universe, where the orange and red dots represent the position of a galaxy, and the circles highlight areas of void. So again, just to show that it is not a homogeneous distribution of galaxies, but there is these clumping and clusters and voids. And in turn, these clumping and clusters and voids will cause fluctuations in the EBL intensity. This fluctuation in the EBL intensity is what he argues could be the cause of the CMB temperature fluctuations. Here he's plotted two 120 by 120 arc-minute squares. On the left we have the EBL and intensity fluctuations with the color bar, and on the right we have the CMB and temperature fluctuations with the color bar. Now these aren't a one-to-one exactly correlated thing. This is not like the same portion of the sky we're looking at. This is just as an example to show how similar these two different fluctuations look on similar scales. And he argues here that these EBL fluctuations could be what causes the CMB temperature fluctuations. Now to look at this more quantitatively, what he does is run some numerical simulations. In these numerical simulations, he generates EBL fluctuations that are on the scale of 20 to 100 megaparsecs, as this is the average scale of clusters, superclusters, and voids in the universe, and then generates what the observation of the intergalactic dust would be under these conditions. In the end, he comes out with these two plots here. Here on the left, in amplitude versus distance, is the luminosity density fluctuation of dust radiation versus distance, and the right is the spectrum of the dust versus distance. And in the end, he measures intensity fluctuations of the dust of plus or minus 0.25 nanowatts per meter squared per steradian. And that results in temperature fluctuations of the dust of plus or minus 60 microkelvin. Now, if you remember before, the small scale temperature fluctuations of the CMB were about 70 microkelvin. So he says, well, given the rough estimates of the input parameters and the simulation, this temperature fluctuations of the dust is a good match for the temperature fluctuations measured for the CMB. He also makes the point that there are other papers out there supporting this idea that there's a link between CMB temperature fluctuations and structure in the universe. For example, he cites this paper here, Extragalactic Radio Sources and the WMAP Cold Spot by Rudnick in 2007. Here is an image from that paper. It's another map of the CMB in black and white. And here in this box at the bottom is a black dot. This is a cold spot in the CMB. And in this paper, this cold spot is linked to a large void in the universe. Just making the point that there are other papers out there supporting this idea that the CMB temperature fluctuations are linked to structures in the universe like clusters, superclusters, and voids. So with those points, he now argues that the temperature anisotropies seen in the CMB can be explained by the dust theory as well, using clusters, superclusters, and voids. Now he looks at the polarization anisotropies in the CMB. The polarization fluctuations he explains using a similar process to this cartoon shown here on the left, where you have these needle-like dust grains that will be aligned in a magnetic field, here with these green lines. And when these aligned dust grains absorb starlight and then re-emit it, it'll re-emit that light as polarized light. Now, if you're familiar with how light is polarized within the Milky Way, like this map shown here, this is a latitude versus longitude polarization map of the Milky Way, he notes that this is an analogous process to that these intergalactic dust grains across the universe will be aligned in large-scale magnetic fields producing polarized light. Now, the strength of these magnetic fields depend on the structure of the universe. For example, in spiral galaxies, it's been measured that there's 5 to 10 microgauss strength fields. But in starburst galaxies, up to 50 microgauss strength fields have been measured. In clusters of galaxies, 10 to the -5th, 10 to the -7th Gauss fields have been measured. And even in voids, there have been magnetic fields measured. That was at a strength of 10 to the -15 Gauss. So there are these large-scale magnetic fields everywhere in the universe, with intensities that depend on the structure of the universe, like clusters, superclusters, and voids. And those intensity fluctuations in turn produce polarization fluctuations, like is seen in the CMB. And with that, he argues that the dust theory can also explain the polarization anisotropies in the CMB. There will be different strength magnetic fields depending on the structure in the universe, which will produce polarization anisotropies. His last thing he addresses is the anisotropy correlation between temperature and polarization anisotropies. He says here that the temperature and polarization anisotropies are correlated because they are both due to the same structures in the universe, these clusters, superclusters, and voids, and thus it would make sense for them to be correlated in space. And with that, he's now gone through these 5 CMB characteristics here and established how the dust theory could explain the CMB measurements taken for each one. Now that was his main argument for the paper here. He makes a few additional points that I'll briefly go over in a second, but going through these characteristics and establishing how the dust theory could explain each one was the main point of the paper. But like I said, there are a few additional points made at the end. In particular, he talks about how if the CMB is in fact due to intergalactic dust and is not a relic of the Big Bang, how this would call into question other predictions or evidence for the Big Bang and how these would need to be addressed. One he talks about is the abundance predictions with the Big Bang. He notes that while eventually the hydrogen and helium abundances predicted by the Big Bang eventually matched up with the observations, the abundance of lithium still does not match with observations. The predicted lithium abundances in the Big Bang theory are still 2 to 3 times greater than the observations. He also talks about the metallicity evolution in the Big Bang theory. In the Big Bang theory, in early times, it starts with materials and stars with no metals, and then as stars age and die and slowly enrich the universe, the overall metallicity will increase. But he argues here that there is not convincing observations for the expected metallicity evolution with the Big Bang, and there hasn't been any non-metal materials detected, even when looking at early redshifts. And the last thing he looks at here is reionization. In the Big Bang theory, at a Z of about 10, neutral hydrogen is rapidly reionized by stars and galaxies. Now he says here that the observations are less consistent with this rapid decrease in neutral hydrogen predicted by the Big Bang, but when you look at Lyman alpha optical depth measurements, that these are actually more consistent with a constant redshift independent photoionization rate. Now we've gone through most of the main points in this paper, and I'll conclude and summarize the bigger points here. In this paper, he looked at a theory that the CMB is not a relic of the Big Bang, but it's instead due to thermalized intergalactic dust. He argues that this intergalactic dust is thermalized by the EBL and would produce a dust temperature of 2.776 Kelvin, which he compares to the CMB temperature of 2.725 Kelvin. He then looks at the frequency and temperature dependencies of this dust with redshift and says that these will exactly cancel out to produce a single temperature black body spectrum, just like we see in the CMB. He also says clusters, superclusters, and voids will produce temperature and polarization anisotropies, and that these will be correlated in space. Which this all comes together to the main conclusion that the CMB could be explained by thermal radiation of intergalactic dust. As for the future of this theory, he notes that more accurate measurements are still needed, like measurements of the EBL, galactic and intergalactic dust, and opacity of galaxies in intergalactic space. And in particular, some of these measurements could be taken with the James Webb Telescope in the future. And it can also be stressed here that if the CMB is truly due to intergalactic dust and is not a relic of the Big Bang, that this would have huge implications for the current cosmological model, so it would be important to get more data for this and investigate this further. But that is all for this video for now. Thank you for watching, and of course a link to this paper is included in the description if you would like to read it for yourself as well.